Thank you. After a small technical error, we're now going to start again. Good evening. Welcome to the July meeting for East Valley Astronomy Club. And it's actually working now. So here we are at our general meeting. Our agenda: welcome, introduction, current business. Our featured speaker is Frede. For his second part of AP is Astrophotography as a Journey. So welcome for all of the folks who are in the meeting here at the library. There are about 35 here, and I think we've got about 30 or so online on Zoom. So it's our combination meeting. Officers and board, my name is Claude Haynes. I'm the president. We're still hunting for vice presidents. Secretary is Gordon Rosner in the back, and Alexandra Nachman is our treasurer, also in the back. And then we have board members. I see Dave. Do we have other board members who are here? I think others are on vacation time. So, oh, okay, Brooks, thank you. There we are, waving in the back, Brooks. James is our property director and is also doing technology for us tonight. Alexandra is our events coordinator, and we will be starting up with some activities beginning in the fall once the monsoon settles down and we have school starting back up. And Marty is our webmaster and our newsletter editor. So a couple of logistics, shirts and hats on the table for the people here in the room. Badges are in the back. And if you have anything else with Alexandra, please see her back in the back. We have a good number of folks tonight that I don't recognize. So do we have any visitors tonight? Okay, if you could stand and introduce yourself. Okay, thank you, Doug. Doug moved from Texas, now lives in Mesa. This is for the Zoom folks. Other people who are visitors tonight. Yes. Okay, Taylor specializes in dad jokes, and he's joined us in the past on Zoom, and he's with us tonight. Anybody else? Yes, sir. Okay, so we have a new member and visitor, and your name again was? Walt. Walt? He came from California. He came from California with a banjo. Oh, okay. All righty. Yes. Yes, we can blame Walt for the weather. Since he moved from California, we've had nothing but clouds. There we go. And there was another gentleman in the back too. All right, Ken is also a new member and visitor. There seems to be a theme here. Okay, perfect, good. Thank you for everybody who is here. We appreciate your being here tonight. And let's have some fun. We do have a summer family event coming up Monday, July 25th. It's a 7:30 lecture with viewing afterwards. Alexandra is doing the lecture this month. It's on the James Webb, the new photos that we've all been seeing. We had a good crowd last month. Gordon gave the lecture. We had also some help with Shane Guffey, and I can move this and read my notes. And now it's not going to let me do that. And Steve Bradshaw, now I remember. Anyway, we had about 60 people, I think, and it was a good crowd. It was a good night. Things tapered off after that, but we're hoping that it'll be better too. But this is in conjunction with the library. And we've done this for many years, but we had to break for the pandemonium. So it's good that we're able to kind of start this again. Behave. All right, and the observatory may or may not be open tonight. The weather permitting is the real key piece there. It's looking pretty cloudy, so if we see Don in the back, we'll know that no, they didn't open up. But do come and visit us. We do try to be open no matter what, as long as we have something to view. The issue oftentimes, though, is here in the monsoon season, things can blow in pretty quickly. If you are interested, we have had a communication from a group that is looking to sponsor a foreign exchange student who is interested in astronomy, math, and physics. He's looking for a host. If you are interested, see Alex in the back. She has the information to help little Miguel. And I want to give you just a heads up. We're not voting on this tonight, but due to the bylaws, if we're going to make any changes in membership, we do need to announce it to the club. So next month, we will be voting on a small change for dues. If you look currently at dues, we did a 4-tiered system, and it ended up with 50 cents and 25 cents and some very strange numbers. So what we are proposing is to make it simpler, $30, no change in the membership, and $35 for family members, and then doing it on a 6-month basis. So it's $15 for the last half of the year, $20 for the last half of the year for family membership. I know some of you do well in math because you do astronomy. It is not an even divide, but we didn't want to raise the dues rate. So the 6-month for the family membership is a couple of dollars more, but it makes it much easier than us having to worry about all of the small change. We're also adding a student and teacher membership, an educational membership, $20 flat rate, January to June, and then $10 July to December. We are also making a change. If you see the last quarter, you would pay for your current year's dues, and then you would be enrolled for the next year. This was really confusing for some folks because they don't remember whether or not they had actually paid. And so since we did a survey by looking at other clubs across the state, and I picked a few clubs in other large metropolitan areas, only one other club does this. So we decided, because it is oftentimes confusing for some of our members, we're just making a statement that everyone's dues renew in January. If in the last quarter you want to give us $30 plus 15, and that now you count, we can achieve that, but we're not going to make it our policy. We're just going to say that it's simpler to do that for renewing in January. Hope that makes sense. You'll see it listed in the newsletter, and then we'll vote on it at the membership meeting next month. According to the terms of the Constitution and bylaws, it specifically states members present. So if you want to vote on that, please come to the meeting, but we can't really do it by Zoom meeting votes. So since I have a captive audience, I figured I would give you an opportunity to show you what I did on my summer vacation. So we'll just take a minute for my slides. I went to the Grand Canyon Star Party, which I would recommend. And let me see if I can get this to work too. That's better. So it's hard to imagine that when you're standing on the rim of the canyon, that this is all only 13,000 years old and created by one major flood event. Yes, hard to believe. So anyway, I went with Don Wrigley. We had a fun time there. We had a good crowd. We had about 50 telescopes. This is the gathering meeting on Monday night. Don's 16 and the edge of my 16 is in the corner. And the skies were really, really nice. And you saw all sorts of different telescopes, including this one called the Light Bucket. It's what happens if you mix your shopping list between Starizona and Home Depot. It's basically 2 5-gallon buckets with a mirror in one end and cutouts for the other. We did solar observing also and met a lot of nice people. Usually, even for foreign folks, there is one person who can speak English. Otherwise, you're doing a lot of pointing and bowing. But the canyon does draw a great variety of people from all over the country. And they were pretty busy considering the end of the pandemic, and so we had a really good crowd. Unfortunately, Tuesday and Wednesday started out this way. Makes for a beautiful sunset, but it's not very fun for observing. However, after about an hour, hour and a half, it did clear, and I should probably turn the lights off so you can see. I left the slide kind of unfiltered simply because you can see how dark it is up there. It really is nice now that they have worked with the dark sky folks, and they have filtered, they counted over 5,000 lights. So they did, one of the first things was to inventory all the lights and to judge their impact. And so you'll see new fixtures all over the park, and it really is a really fun place to go visit. So I would recommend the Star Party. And then we saw something up there that we are working on as a project for the observatory. We want to start a larger meteorite collection at the observatory and display them in a case kind of on the outside of the building. So if you guys have any spare meteorites lying around and would like to make a contribution to the project, or financially, if you'd like to help us, just contact Alex and you can make a donation. It's probably going to be a little expensive, but we think that it would be a good addition to the observatory to add another larger collection of meteorites. And then we went to Flagstaff. This is the back of their new GeoVale dome. And I took the picture this direction. The front half you see there with the circular windows has a large door. It opens up and the building slides backwards over the back half. And then that's where these telescopes are mounted. So they have a number of telescopes there. Our speaker for September is going to be Director of Development for Lowell, Kevin Schindler, and he's spoken to us before, but they're doing an awful lot of work up at Lowell, and if you haven't been for a while, I really would recommend it. It's a great place for your summer vacation.
Let's start here. I will reintroduce myself for the camera. I'm Sid Frede, and I'll do my joke over again. I'm an amateur astrophotographer, and that may sound like an addiction, and it probably is, because astrophotography can indeed be addiction. And I must admit that I'm an astro junkie. So what I'd like to do is to review a little bit about what we talked about last time and get into some new material tonight. So basically looking at three phases of astrophotography that involves capture, calibrate, and create. The image capture part that's the telescope and the mount and the controller and the filters and the guides and the exposures and all the mechanical things we put together to take that one image. Tonight, we're going to talk about image calibration as well. That's taking that light frame that we've captured, talking about light frames, bias frames, dark frames, flat dark frames, dark flat frames, all extremely confusing. It took me quite a while to get my head around all of that. So we'll try to simplify that and take some of the mystery out of it. And finally get around to actually creating that image, which is the whole purpose of this exercise right now, is to come up with that astro image that we could be proud of. This is my very first deep sky photographer. You might be able to recognize it. It's supposed to be M42. You can see that it's horribly out of focus. It sort of looks like what the Orion Nebula might look like. We've got some reds in there and some hydrogen alpha, and that was what got me hooked. After I took that photograph, I thought, well, this is wonderful. This looks marvelous. What can I do next? Well, I needed a telescope. So Celestron was having a sale early in 2020, right before the real height of the pandemic. And I bought an edge scope and a equatorial mount and got started and then started assembling all my system. Well, first of all, we need to be able to talk to the system. So I loaded up my ASCOM drivers, which is a standard industry platform. And almost all the equipment manufacturers also have ASCOM drivers as well as native drivers, so you can actually talk to the equipment. And then connecting them up electrically was something that wasn't all that difficult for me. My background's in electrical engineering, so I finally got to something that I could understand. Basically talked about a hub, USB hub, where all my equipment plugs into. And I have basically one USB cable coming out to my PC, which is sitting on my patio table. And of course, a power supply to power the PC and a power strip that powers a 12-volt, 10-amp supply, which powers all of my equipment. So basically, I can sit on my patio with my PC, one connection to all of my equipment. Wrong way. Once I got the equipment set up, the connections, I'm ready to go. So I'm powered up, and now I'm actually working on the telescope. So one thing I needed to be able to do is to be able to point it at something I could recognize. And almost all mounts have a hand controller, And with that hand control, you have an alignment process, which basically go to 2 or 3 stars, center on the star, sync to that star, and from there on, the telescope knows where it's at. So now you can say, I want to go to the next target. The telescope understands where it's at and where it can go. And now you can zoom around the sky and take a look at a lot of objects at night. However, if you really want to talk about photographing, you've got to be accurately aligned to the North Celestial Pole. Otherwise, you're going to have stars that are out of round, elongated stars, and not very good tracking. So once I got through that, I spent about the first 6 weeks of my system doing observation, learning about the mount, the eyepieces, the alignment, polar alignment, go-to alignment, going through the sky to all sorts of targets, getting a sequence down where I could tear down my scope and set up my scope and store all the pieces. So I sort of had a template, if you will, in order to be able to get everything running, and then fine-tuning all the cabling and connections so nothing caught and it would actually work. And now I'm ready to take some pictures. Well, my very first camera was my Canon DSLR. Almost everybody has a Canon camera or a Nikon camera or a Sony camera or a Minolta or something. And almost all those cameras you can directly connect with an adapter to your telescope. And that was what I took that very first photograph with and started experimenting with that. They're powerful CMOS sensors. They're very good astrophotography cameras. And you can go a long way and take a lot of really beautiful photographs with your DSLR camera. But then I soon moved into a dedicated astro camera. And really what that brought to the party was being able to address a cool sensor. So you can actually cool that sensor down to probably 30, 35 degrees C less than the ambient, which greatly reduces some of the bad aspects of the sensor that I'll talk about later. They're targeted towards astro, large selection, a lot of people build them, reasonably priced, they're really good cameras. Well, one thing I soon found out that you can have the best equipment, but if you're not in focus, you're recording garbage. You got to be in focus. And to do that in astrophotography, it's really helpful to have an autofocuser of some type. And they're relatively inexpensive. And basically the way an autofocuser works is that you start out somewhere close to what you think is focus, turn the focuser on, and it goes and it displaces itself mechanically a certain distance by turning the knob, which is attached to my focuser, and recording some data points. And then it goes the other direction, records some more data points. The computer goes to work, determines what a parabolic function fits those data points, and then this point becomes your most accurate focus. Works extremely well. And I also started out with the batten-off mask, which many people are familiar with, and it correlated very, very closely to the automatic focuser. So I got some confidence that my automatic focuser was working and I was getting correct focus. And basically I could turn that loose all night long because changes in temperature, changes in seeing conditions, changes in positions, all sorts of things can affect the focus. And if you're not regularly refocusing, again, you're recording garbage. Exposure. Now we get into religion and politics, a heavily discussed item. And what's the proper exposure? What's the correct exposure? Well, the proper exposure is when it's enough. And how do you determine that? Well, there's lots of things on YouTube that you can look at to help you with that, but basically it becomes experimentation. And for me, I'm in Tempe. My observatory is my backyard patio. I'm in a borderlight sky at best, which is pretty horrible light conditions. And for my particular setup of my camera, I found that for doing RGB or color, I typically expose about 60 seconds or 120 seconds per frame. For narrowband, I'm exposing 300 to 600 nanoseconds per frame. That's probably fairly typical for a lot of people, and certainly in my sky conditions, it works and works well for me, so I've kind of settled on those particular parameters. And lots of discussions about, do I take lots of exposures with very short durations, or do I take only a few exposures with longer durations? And the answer to that is it depends. And typically in light polluted environments, you're going to take a lot of short exposures because the light pollution is such a large factor, it quickly overwhelms your target. In dark sky conditions, since light pollution is not such a factor, you can expose for a longer period of time and collect a lot of data without having the light from the pollution bother your exposures. This is probably familiar to a lot of people. This is Pillars of Creation from the Hubble. And Hubble exposes in what's typically known as the SHO palette. And what they're basically doing is that for an emissions nebula, there's some very specific wavelengths that come out of that initial nebula based upon the ionization of the gases that are there. And that is a sulfur, hydrogen alpha, and oxygen, therefore what's called the SHO palette. And to the eye, this is not what we would consider to be a true color. This wouldn't be necessarily what the eye sees, because we see blue, green, and red, put those all together, and that's visually what the eye perceives. So when we talk about the Hubble palette, it's a little different than what visually we might see ourselves. But 4 things to make you look like a pro. Plate solving. When you do a go-to alignment, after 2 or 3 stars, you're pretty well assured that when you go to the next target, that target's going to be fairly well centered in the frame of your eyepiece or fairly well centered in your camera frame. You know, the systems are really good today. Once you tell a telescope several reference points, it knows where it's at, it goes to another point, it knows where it's going. What plate solving does is it basically takes an image and then compares that to a known database, whether it's something that's stored on your computer or whether it's something that you go to internet online. And it basically says, I recognize that, but I'm not exactly centered. So it'll send a command to your mount to nudge it a little bit to bring that target towards center. It'll take another exposure to find out if it did it right. And they say, well, we're not quite right yet. So we'll send a few more commands to the mount to make sure it's centered. And I found that for my system, which is probably pretty typical, a couple iterations of the plate solve puts that target dead center. It's right in the center of my camera frame, exactly where I want it to be. And a couple of plate solves takes maybe 2 minutes, maybe 3 minutes, and you're right on target. Dithering, again, we send some commands to the mount to displace our image a few pixels in one direction, or maybe 2 directions, every certain number of frames, maybe it's every 4 frames. So what we're doing there is trying to help the software identify things like stuck pixels or hot pixels in our sensor so that the software knows where they're at and then later can take them out. Flip, I'll talk about in just a minute. Scripting, almost every capture program has the ability to put into a script the manual steps which is used to get where you're going. For example, I'm going to cool my sensor when I start. I'm going to do a go-to. I'm going to do a plate solve. I'm going to start my guiding. I'm going to start exposure. I'm going to finish exposure. I'm going to start this all over again. Well, you can put that into a script and punch go, and your software will take you through those steps and execute all those steps. The meridian flip is scary. For just getting started in amateur astrophotography, you're ideally tracking a target, picking it somewhere up in the east, getting a lot of exposure time as it gets pretty much overhead. We now have to do a meridian flip, which is called, to reposition our telescope to catch our target so we could follow it over to the west and finish our exposures. This is an example of what's happened in that my target started out in the east. This would be east, which it is tonight. We start out in the east. It followed the target up towards the meridian, which is directly above it. And the meridian is basically a line that goes through the north celestial pole to the south and divides the sky into the east half and the west half. So when we get to this point, my scope can no longer keep tracking because I have a problem. Down here, which is not shown, I have my image train, which is my focal reducer, spacer, my off-axis guider, a filter wheel, and my camera. And if I continue to go ahead and try to track that direction, I have a problem because over here I have a tripod leg. And the first thing that happens is my camera, it's a tripod leg, breaks my camera off, causes the tripod leg to collapse, and my whole system falls on my patio. Not good. So what we do is a meridian flip. And pardon the juggling here, but this is my iPhone. So I've reached the meridian, I tell my camera, go to the target, which is now on the west side of the sky. My software knows that the target's over on the west side of the sky, so I'm going to go to that particular position. This is real time. So my scope is getting ready to reposition itself. It's now going to go look for the target in the western sky. So I've done my go-to, high probability that my target is fairly close to the center of my scope. I'll wait for about 30 seconds. There's the delay so we can eliminate the vibrations of what I just did mechanically. Then I'll do a plate solve again, to make sure I reposition my target exactly in the center of my frame. After my plate solve is completed, I'll restart my guiding. We'll talk about guiding in a minute. Let that settle for about 30 seconds so it's stable. And I'll start taking pictures again. And now I can follow my target all the way through the western sky until the point in time whether my target drops below the horizon or the sun comes up. So what I've been able to accomplish is that all night long, I can stay on target from the time my target first rises when the sun goes down, all the way through the meridian to the point in time where now my target disappears when the sun's come up. So I can get a lot of imaging time on a particular target that night. Well, we're talking about imaging a target. How do you find a target? A number of ways to do that, but first of all, we have to have a coordinate system that very specifically defines where our target is, down to the arc second, or to about down to the decimal points of an arc second. And then once we define where the target is, we need some type of planetarium software or a sky atlas or something basically to determine what it is we're trying to take, how big it is, what the parameters are, and is it something I really want to image this night? Coordinate system. This is something that really took me a while to get my head around. And there are a couple of YouTube videos here that are really, really excellent. But basically our coordinate system to identify our target is the RA axis and the deck axis. And RA is right ascension. And it's a number of hours behind the sun that our target is on March 21st at the vernal equinox. Well, what does that mean? I'll try to visually show you that in a second. Declination is the angle of our target when it's passing through the meridian, when it's directly above us. Now, with a particular target as my example, I'm going to look at the Crescent Nebula. It has an RA value of, we'll basically look at the first digits of 20 and a declination of 38. Well, the declination is the easiest to explain. So we basically take the declination of our target and the declination that we are here in Arizona, which is about 33 degrees. So we take 38 minus 33, we come up with positive 5. If we have a positive number, that means our target is north of our point directly above our head. And 5 degrees says it's 5 degrees north. So our target, when it passes through the meridian, will be directly above my head and 5 degrees up in the northern sky. So that very accurately defines the declination of my target. Let me try this. RA, or right ascension. So it's the number of hours our target is behind the sun on March 21st. So let's say our target is 2 hours behind the sun. So I'm going to do some little gyrations here and try to, you can hear me. But if my sun is now at sunset or at 6 o'clock, and my target is 2 hours behind the sun, so basically, again, it's the number of hours behind the sun that my target is on March 21st. Well, we're continually going around the sun for 360 degrees. So every month we're traveling 30 degrees. And we're also during that time basically changing 2 hours every month. Our particular target, I'm going to look at tonight, has an RA of 20. So what that means is that it's 20 hours behind the sun on March 21st. So if the sun is here, there's 6 hours, 12 hours, 18 hours, and 2 more hours. I'm 20 hours now behind the sun. You also might look at that as I'm actually 4 hours ahead of the sun. So as the sun is moving, my target is moving 20 hours behind the sun. Well, that's on March 21st. On April 21st, we changed 30 degrees or 2 hours. So it's now 18 hours behind the sun. On May 21st, it's now 16 hours behind the sun. On June 21st, it's now 14 hours behind the sun. And on July 21st, which is about now, it's 12 hours behind the sun. Well, that's pretty convenient because when the sun is setting, my target is rising. It's now dark. And as the sun is rising, my target is setting. So if I want to pick a target in July that has the most exposure at the night, I'm looking for a target that has something in the range of an RA of 20. And again, those two particular videos, one on right ascension and one on declination, are extremely helpful and extremely visual. And the gentleman who does that is Mr. Wizard. He's Mr. Math, Mr. Physics, Mr. Astronomy. Has a whole series of online lectures and really, really good, but certainly a great reference. So let's take a look at this. Let's take a look at that target. So what happens for this particular target? So on July 15th, which is tonight, that target at 1:04 a.m. and 19 seconds will cross through the meridian at 5 degrees to the north. So if you want to go outside tonight at 4 minutes after 1 and look at 5 degrees to the north, that's where the Crescent Nebula will be. Now, from a planetarium software standpoint, if you're familiar with Stellarium, there's a website called Telescopius, astrocom.bin. If you haven't been there, I highly recommend it. This is where amateur astrophotographers can post their images, and you can look at something like the Crescent Nebula, and there are photographers from all over the world who have published their images. It has a great query capability, so if you want to say, well, I want to see all the images of the Cocoon Nebula that have been taken with my telescope and with my camera, you can do that search and you get a whole list of images that are posted. And you can take a look at, well, how did he do that? What was his exposure time? How many exposures did he use? What kind of filter did he use? What was the sky conditions when he took those images? A great, great tool to plan your own particular exposures as far as determining what's there. And this will be posted, of course, on our website. And all these links are typically live and clickable. Sky Safari is a program that works on iPads and iPhones, and it's one that I use all the time. It's very visual, tells you where everything is in relation to everything else in the sky. You can do all sorts of searches, a great little program, and I think the entry level is free, and they maybe have a little upcharge for their pro version. And another source is James. James publishes every month a very detailed list of targets that are prime targets for that particular month. All sorts of information, data, also has photos and links. I go there every month and I'm taking a look at targets to track the image. A great source of information from one of our local astronomers. I use Nina as my capture program. And in Nina, it has also a Sky Atlas, which is basically a planetarium program. This is just a screenshot from Nina. I said, well, show me the Crescent Nebula. I said, well, that's also NGC 6888, or it's also called LBN 203. It gives me a pictorial representation of what the Crescent Nebula looks like. It says, okay, here's my RA and my deck, which we just looked at. It's also described as a bright nebula. It says it's about 20 arc minutes in size, which tells me, well, that's a good idea because I know that my camera frame will take about 50 arc minutes, so it'll fit in my camera frame. And oh, by the way, at sundown, it's at about 50 degrees, which is good because I'm not shooting through a lot of atmosphere. And when it crosses the meridian, it's at 85 degrees. Well, that happens to be 5 degrees at the north we just talked about. And then it continues on until sunup, and it's still about 50 degrees in the sky. So it's a great target to image this time of the year. It's available all night long. You're shooting through a minimum amount of atmosphere. And of course, the best time to shoot a target is when it's at the meridian, because we're shooting through the minimum amount of atmosphere. So we have less disturbances going on. So this is a great target image right now. Also in the Nina, I just said, well, show me some targets within the range of about 18 to 20 RA for this particular time. And it gave me a whole list of several hundred of nebulas and galaxies and dual stars and variable stars. And you can sort this list by all sorts of criteria. And again, it says, okay, my meridian is going to be somewhere around midnight. The target's going to be in the sky almost all night long. So let's take a look at some of those targets and see if they're ones I might want to chase. And if I'm interested in it, I might go to another planetarium program, take a closer look, run over to James's programs, take a look at what he has to say about it, and continue from there. This is my own invention to try to get my head around organizing and analyzing where these parts are. So this is basically sunset. This is my sun traveling around. So this is midnight. And then this is the dark sky. And this is the meridian. So if I want to find my targets that are in the latter part of July, I've placed that on my meridian. take a look at my arrow and it says I need an RA of about 20. Let's say I want some targets to image in October. Well, let's move October about, there's 1 click and 2 clicks and maybe 2.5. So if this moves with 1, 2, and 2.5, it says my RA value is about 1 or 2. So if I want to image targets in October that are in the sky almost night long, I can pick an RA of about that value. Well, I made myself a little table, and again, talked about the RA changes 2 hours every month because of the Earth moving around the sun. For any particular month, if I want to image a target that passes the meridian about midnight, there's my RA value. And that's one of the ways I start taking a look at potential targets that will be coming up, because as soon as we get through the monsoons, I'll bring out my telescope again and start taking a look at maybe getting something in September if some of the sky is cleared a little bit, but certainly October and November, need to start taking a look at targets that I want to try to chase in that time frame. Also on those programs, they have some framing capability. And this basically maps out the size of my sensor. And it shows me that, I mentioned that this was about 20 arc minutes and I can handle about 60 or 50 or 60. It shows me, oh, that's well framed. I can certainly fit that in my camera. This is Stellarium, has the same type of a thing. You can put in your sensor parameters, tells you where the product is framed. This is the on-site website Dimension Telescopius, does the same thing. You can put in your sensor values, and for any particular target, it will show you where that particular target will show up in your camera. Guiding. Talked a little bit briefly last time about PhD2, and that's kind of a universal guiding program that many, many people use, and that stands for Push Here Dummy. It's primarily tended to be kind of a one-shot deal. Line things up, press the button, let the guiding software take over, and it goes from there. Well, since the last month's presentation, I had a couple of questions, and one was about, well, is my guide star the same as my target? I mean, do I have to have my guiding to 0 on my target to track my target? Well, no, it almost never is your target, because there's a couple of methods of doing guiding. One is with an external scope, and one is on axis, and I'll talk about that. But basically, if you're properly polar aligned, if you're looking at your target, and let's make this my target, and I pick any guide star, and as that moves around this north celestial pole, if my guide star is properly polar aligned, it'll follow my target exactly. And if my guide star is not properly aligned, you're going to get some stars out of round, some stars that are bloated, and you'll see that very quickly. Typically on the mounts that we use as amateur astrophotographers, they're pretty good about an exposure up to about 30 seconds. As you start to reach 60 seconds or so, you're going to start getting some lagging behind the tracking. And that's when your stars start to blur a little bit. And that comes out of focus. And that's when guiding is really required. Now, there are many systems that have the ability to track your target without any external guiding. Astrophysics entry-level mounts about $10,000. For a couple $1,000s more, you can buy some encoders, and you can track without an external guider. Ioptron has similar versions, and for $10,000 or $15,000 or $20,000, you can get a system that will guide for you. And then 10 micron has some systems where you can get up to $20,000, $30,000, $40,000 for a mount, and it will do fine without external guiding. Well, that's a little outside my price range. And it's typically more for the scientific observer or the astronomer, where they're doing some very specific instrumentation. But for us, we have a cheaper way of doing that. One is an external guide scope with a camera. That's small and it's inexpensive. And when we start getting to longer focal lengths, we go to something called the off-axis guider. So let's take a look at those. This is pretty straightforward, isn't it? These are a couple of logs from PhD2 from 2 different nights that tells me what my guiding is doing. Now, ideally, if we're looking at this, the blue track is my RA axis, and that's my axis that's going around the north celestial pole. And the red chart is my declination axis, or that's my axis that's following the target. Ideally, in a perfect world, both of those lines are straight lines right through the middle. That'll never happen. You got conditions with changes in temperature, changes in seeing conditions, and just the accuracy of trying to stay on target. But what does happen is that if you can see, and I hope you can, and that we're looking at the blue graph, when it goes above the line, we've got a couple of pulses here. So the guider says, okay, we're getting out of whack right here. I'm going to send some pulses to the mount to bring that back down. So it does bring it back down, but it overshoots. So then it goes and gets another pulse, and let's go the other direction, and we'll go the other direction. So what you've got is all night long is you've got this up and down, up and down, up and down, because the conditions are continually changing, and your guiding software is sending commands to your mount to try to keep that guide star exactly where you want it to be, so your image is nice and sharp. So these are identical situations as far as the equipment and the parameters set up on the guiding software, but you can take a look at the one at the bottom, significantly different results. What's happening here is that my RA axis is doing pretty well. I'm getting guide pulses to correct for the shooting up above and below the line, but my deck axis is way out of whack. I'm way down here, and you can see my software is throwing a pulse all the time, trying to get this thing up and get this thing up. And that may happen for a while, then it might go away as conditions change, but typically you can adjust for that because PH2 has something called guiding assistance, and you can turn that loose, let it run for 5 or 10 minutes, and they'll make some recommendations about changes in the parameters that will improve this guiding. And then we got something over here. What happened here? Boy, did things go crazy there. Well, if you remember, I talked about dithering, where you purposely take the amount, a number of pixels off the target, take an image, and then come back again, and then use that later to adjust for some of the bad effects of our sensor. What happened right here is we had a dither. We purposely drew them out so many pixels off the target. It says, whoa, what happened there? So now it's struggling really hard to bring it back in. So for a period of time, this settles until we get back to some type of stability, and then we resume guiding and imaging again. And that is a parameter that's settable in your software. Oftentimes it's 15 seconds, or maybe it's 30 seconds, or depending on the criteria. But after you do that dither, you want to give it time to settle before you start imaging again. This is a typical setup for a external guide scope. Normally we take a look, kind of a general rule of thumb, at that the focal length of the guide scope is about 1/4 of the focal length of your imaging scope. In this particular case, if we're imaging with a 400 millimeters image scope, 1/4 of that's about a 100 millimeter guide scope. And most of our guide scopes in the range of 50 millimeter to 100 millimeter guide scopes. And there are a lot of manufacturers. They're relatively inexpensive. They work really well, and they're great little scopes. If you start getting larger focal lengths, you start running into some performance issues. This particular, it's a 100 Skywatcher. So that must be about a 900 millimeter focal length scope. So we see we got a pretty good sized guide scope up here. That's probably about, maybe excess of 200 millimeters, maybe 250 millimeter guide scope. Now we're starting to get fairly large. So what happens, if we get into larger focal lengths, that size and weight of that external guide scope becomes prohibitive. Now we've got, if I'm guiding at 200 millimeters, which is about what I'm guiding at right now with my images, that means the quarter roll, I need a 500 millimeter guide scope. Well, a 500 millimeter guide scope will run you about $1,000 easily, and it's going to weigh a lot. And the problem with the weight is that flexure becomes a problem. And what is flexure? Well, my scope is a Schmidt-Cassegrain scope, which is basically an aluminum tube with a couple of mirrors inside. So if you put a big weight on that aluminum tube, the aluminum tube bends. If the aluminum tube bends, the mirrors go out of focus. You lose focus, you get parallax, all sorts of problems. So on larger focal length scopes, especially Schmidt-Cassegrains, you really can't use an external guide scope. It's too expensive and it's too heavy. So how do you solve that problem? We go to off-axis guiders. And what's an off-axis guider? This is the off-axis guider that I use. It has a prism, a right-angle prism, which inserts itself into the image train. It looks something like this, and it sits right here on the image train. And there's my camera for my guide camera. So what we're trying to do is that we insert this into the image train. You'll notice that it doesn't obstruct the sensor in my camera. There's plenty of room there. We have a cylindrical image train, and we have a rectangular camera sensor or a square camera sensor. So we can drop this optical right-angle prism into our image train and pull off a piece of that light. And if they're lucky, that piece of that light will have some stars in it, which our camera recognizes in our guide camera, and that's where we guide our system. Now, there's a critical dimension here in that the distance from the prism to the sensor in our camera has to be the same as the distance from the prism to the sensor in our guide camera. That means that when our image camera is in focus, our guide camera is in focus, and our guide camera can then get a nice clear star to zero in on the guide with. Works very, very well. It takes a little setup. You have to be sure that you're not getting too far down in the image train of blocking the image coming back into your camera, but that's fairly easy to do. It takes a couple iterations and a couple experiments, but once you've got it set up, you basically never touch it. Now, the one problem you run into, or can run into, is that, I don't know if you can, this is again the stellarium, and this is the outline of my camera, and then this would be the outline of my guide camera. Because again, we've got this prism, and we're only taking off a very narrow section. And what we're hoping to have is that when we look at that image, we have some stars in that particular area that we can latch onto and guide with. It's possible that there won't be enough stars there. In a couple of years, I've only had one instance when I had a target where I couldn't find a guide star. So what you do there is you basically take this off-axis guider and let's say move it 90 degrees in relationship to the camera, and we'll move it over here and hopefully we've got a guide star. So that might be the adjustment you have to make. I have to say, I've done that once in 2 years. Otherwise, the important thing here is to have a really good guide camera with a nice big sensor. So if there are stars in that field, it'll find them and it can use them. And PHD2 also not only picks up a single guide star, but now it has multiple star guiding. So you can have as much as a half a dozen stars that it locks onto a guide with. It's very accurate. Here's where we run into some problems. Here's a Smith-Cassegrain scope, probably pretty similar to the one I have, with a guide scope on top, which probably weighs 12 pounds. That's going to be a problem. It's going to bend this tube. Here's a scientific installation, which is really pretty incredible. This is a pier-mounted installation. This is a 10 micron, I think, mount. Probably good to handle a couple 100 pounds of weight. And of course, what we're trying to do is to balance everything we have on top with our weights so that when we have our camera over here and our weights over here, it's balanced. So when the guide or when the mount wants to move our camera, it's moving a balanced weight. But the problem still is that we have an inertia to overcome. Well, this is a big horsepower situation. So this is a very expensive Takahashi image camera. We've got another Takahashi image camera set up here. Both of them have cameras and filter wheels. We've got a bunch of scientific equipment stuck on top. It'll work. Probably works pretty well because this is a big mount. But this is something we will probably never see. One problem you have is that when you start stacking cameras like this, the center of mass moves out this direction. And ideally, you'd like to have the center of mass to be the center of your imaging scope. Well, we've got 2 imaging scopes. Well, where's our center of mass? Probably don't really care. But individually, we do care. And this is a pretty good solution for people who want to use 2 scopes at the same time. Here's a couple of scopes, different focal lengths, getting a different image, and they're on a parallel plate. And now instead of having scopes stacked on top, they're next to each other. Our center of mass just happens now to be at the center of both of those imaging scopes. You know, a much better situation for the amateur if you're going to stack more than one scope. Image calibration demystified. This is another area that took me a while to get my head around. And you can spend a lot of time on YouTube looking at the discussions of that. And almost every discussion you see is going to be contradictory to some other discussion. But I locked into a couple of people. Adam Block is a great YouTuber. He works down at the University of Arizona at Mount Lemmon, actually. And he has a series of tutorials that are excellent in describing what's going on here with calibration. And in fact, I borrowed from him some of his diagrams, and he gave me the permission to do that. This is something I did at this July meeting. It's about a 20-minute discussion on calibration. I'm going to take about 5 minutes and summarize that tonight. But before I do, I need to normalize some data because we have different cameras, different processing software, different image creation software. So it can get really confusing if we don't have some common area to talk about. If we take a look at cameras, an 8-bit camera has 256 divisions. That's basically 2 raised to the power of the bits. For a 16-bit camera, we have 65,536 divisions. Well, what that means is that we take black, give it a 0, and we take white, and we give it a 1. We've now entered the digital world, 0s and 1s. So we're never getting any blacker than 0, and we'll never get any whiter than 1. So for these cameras, black is 0, white is 1. The software doesn't care. It's now normalized. It operates on the software in that manner. Now, when we take an image, This particular range is like black is here, this is 0, and 1 would be over here, this is white. Most of our data exists down here. We look into the sky, especially in a dark sky area, it's full of light. The Milky Way is brilliant and the stars are all over the place, and wow, you almost have to close your eyes because it's so bright. But realistically, it's mostly black. And for most of our photographs, if this is 65,000 for my 16-bit, most of my data is down there, but somewhere between 100 and maybe 2,000 or maybe 3,000 at best. So, you know, I'll take a look at what that means here in a little bit as far as stretching and viewing that data. And now we get into the good, the bad, and the ugly. When you take an image, take an exposure, you're getting all three. You don't want all three. What we want is the good stuff. And that's the photons from our target. That's what we want to make our picture out of. What we get is not only the good stuff, but we get the bad stuff. Anytime we put power into a sensor, we've got electrons flowing around at the speed of light. We've got noise occurring, bias currents occurring. We're generating thermal noise. We're generating hot pixels. We have some pixels in that sensor that are very hungry. Anytime an electron flies by, it's going to grab it, and it does what is called as filling up its well. When its well is filled, it becomes, instead of a 0, it becomes a 1, and it stays there. So we have to have a mechanism to get rid of that, and our software and the dithering we talked about helps with that. We've also got the ugly, and these are the optical aberrations in our image train. These are the pictures of the dust on our filters or on the camera surface or on our corrector plate. These are the vignetting that we see because, again, our image train is circular and our sensor is square. So oftentimes we'll get some vignetting on the corner of our picture because of the difference in the optical train and our sensor. So how do you get rid of those? This is a typical light frame, and these are out of proportion to be able to show you what's going on, but the bias and the dark current is what's contributed by our sensor. Whenever we power that sensor up, that's the bad stuff that's going to be there. This is our signal, our good photons that we want, and also the photons that are coming from those optical aberrations that are part of that. So how do we get rid of those? We do calibration frames. And basically, we take a picture of the bad, and we take a picture of the ugly, and we subtract it out, and what we have left is the good. And how does that happen? And again, thanks to Adam Block for letting me use this. But here's our initial light frame. And let's say during the night, I took 100 light frames. And every one of them has the good and the bad and the ugly. About every 3 to 6 months, I take master dark frames. Well, what does that mean? I set aside one night where I expose like 25 frames at 60 seconds, at 120 seconds, at 300 seconds, and 600 seconds, which are the typical exposures I'm going to use because of my experience, at the same temperature that I'm going to be shooting, whether it's 5 degrees or minus 10 degrees or 0 degrees, and basically build a dark library, which I use whenever I'm calibrating my light frame. So a dark library that I created back maybe in January, I'm going to use now to calibrate my system in July. So what that allows me to do is to take the dark frame, again, at the same temperature and the same exposure of my light frame, and let's say this was 120 seconds, and I'll subtract that from my good, the bad, and the ugly. Well, I got rid of the bad, and now I'm left with the good and the ugly. Well, how do I get rid of the ugly? Well, I take a picture of the ugly. And by doing that, we do what we call a flat frame. And here I take an exposure at a fairly high intensity, so I get a lot of definition in that bad stuff. And typically, again, if 0 is 1, and I mean, if 0 is black and 1 is white, I want to take an exposure about 0.5, somewhere middle of that. And that will allow me to take a picture of the ugly stuff. And I'll take the ugly stuff, take it away from the bad, or the good, the bad, I'm sorry, the ugly and the good, and that leaves me with the good. I finally got to the point where now I have an image with only the photons from my signal that I want to keep. This is a typical single light frame, and it's stretched. And what I mean by being stretched, if you remember that histogram from 0 to 1 where most of our signal was over to this side, basically what the software does is it takes a look at that and says, okay, well, I'm going to take that from 500 maybe to 3,000. I'm going to make the 500 0, and I'm going to make the 3,000 white, and I'm going to display that so you can see what you've got. And this is what we have. This is M51. We can see a couple of cores of the galaxy. We can start to see some definition in the spiral. And we say, okay, well, that's a pretty good single light frame. I know that came out pretty well because I've got some data there. Dark frame looks something like this, salt and pepper. Looks kind of ugly, right? All those little dots are those ugly hot pixels I talked about. Those are those pixels that found that electron whizzing by and filled itself up, and it became a 1, it became white. So our software helps us get rid of that. A flat frame? Well, here's some pictures of that dust. That was a dust mote on maybe our filter or maybe our sensor or corrector plate or someplace, but that's ugly. We got to get rid of that. We're also seeing a little bit of vignetting here in the corner, again, where we got the round image train and we got those rectangular sensors. So we're going to get some vignetting. And I know I mentioned before where we drop that right angle sensor into our image train on an off-axis guider. I dropped it a little too far. So you can see this little dark band across the top. That was my fault. So I need to go back and maybe raise that up just a little bit. But taking the flat frame, it will calibrate that out. And for the stuff I'm doing right now, it'll disappear. But in future exposures, I took and moved that up a little bit, so that wasn't a problem. So basically, it sounds complicated, but you basically take those frames that you took, the good stuff, the bad stuff, and the ugly stuff, you feed it into the software and punch go. Deep Sky Stacker is a great stacking software to do that. Doesn't cost any money, it's free on the web. Basically, we load them into that and say go. There's our picture files, which are light files, dark files, flat files, and dark flat and flat dark, which I didn't really mention, but I talked about whenever you power up a sensor, you're getting the dark stuff. Well, we powered up that sensor and we took the light frame because we're taking it about half of our total intensity. So there is some dark stuff in there that we want to get rid of. So I take an exposure at the same time as the flat frame, which is about a second at the same temperature. And again, the software takes care of that and gets rid of that. It's a very small part of the flat frame, but if you're going through the process, it's easy to do and the software does it for you. So what it winds up with is a master light frame. So here's an example. A particular night, I took 133 frames at 300 seconds in 3 sessions over 6 nights on M51. I had 40 dark frames in my dark library at 300 seconds at the same temperature. I took 40 flat frames at about a second, 0.95 seconds. I took 40 dark flat frames at 0.95 seconds. Loaded those into the software, and it creates a single master light frame. So that's what this looks like. This is an unstretched single exposure, and it's black, right? Because we're taking mostly pictures of black stuff. And what we did was stretch it. And now we take maybe that 100 to the 3 or 4,000 or 4,000 or wherever our light exists. We make one end 0 and the other end white. And now we can see what we've got. Now we can see the structure of our M51. We can see the 2 galaxies. We can see some structure on the spiral arms. And say, okay, that's a pretty good light frame. That's probably going to work out well. So we take those 253 frames, the 133 light frames we took, and the 25 darks and the 40 of whatever and 40 whatever, and we take that and we feed it into our software and we get this. I want to say, well, that looks pretty good. I've got a lot of nebulosity here. I've got the spiral arms. I can see some detail there, but boy, there's no color. Well, that's where the processing software comes in, because we can take Photoshop, or in the case I use PixInsight, maybe finish off with Photoshop, and you tease the color out of it. So you tease the color out, you turn down the noise, do a bunch of combinations and modifications to it, and you get a pretty picture. And that's what we were trying to accomplish all along. Here's another example. This is the Rosette Nebula, the stretched single frame. Okay, I can see a bunch of stars, but there's not much detail there, right? Well, if you take a look at the end image, there's not a lot of contrast. We take a look at the single frame that's produced from all the software. That's our master light frame. Now we can say, okay, I recognize that. I can see some color in here. We can probably pull that out nicely. And you can run it into Photoshop or PixInsight and wind up with a nice, pretty color picture. This is a Horsehead Nebula, really famous nebula. And in the single exposure that's stretched, we can start to see some definition of the Horsehead and the background, because there is quite a bit of contrast here. The dark nebula is very dark and our background is very hydrogen rich, so it's very bright. This is a single master light frame when we combine all of our software. You say, well, that's kind of okay. My stars are kind of a weird color and it's pretty noisy, and what happened to my color? Well, again, into Photoshop or into PixInsight, work through that process and we come up with our final image. So I go back and I look at that as well. I did this over a year ago, and what I've learned so far, I see some things that I could do better. So every exposure I take and every image I process, I learn something. And you can go back and say, well, I can improve on that and I can change some things and we'll try better the next time. Here's another one. This is a Leo triplet. We can start to see our 3 galaxies and the cores. A single master light frame has a little more definition, but again, not much color there. But once you're through with it in Photoshop or PixInsight, whatever you're using, there's a whole variety of programs you can use. You wind up with that final pretty picture. And here's where we get into science versus art. The science part, I was pretty good at, actually. You know, my background's in engineering, that's the part I understand. That's the telescopes and the mounts and the software and electrical parts of the connections and everything that goes together to put together a system that allows us to capture an image. The art part, I'm not so good at. You know, I get a decent eye for composition and colors and framing. I shot a lot of DSLR photos over the years, but really when it comes to the artistic flair, my drawing skills are pretty much stick figures. I don't go beyond that. But the software allows you that flexibility to really take an individual journey, and color calibration and background extraction, noise reduction, all those types of things you get involved in allows you to produce an image that's your image. And there's no such thing as a wrong image from the data that you produce, because everything is individual. This is a screenshot from Astrobin of M42. And I think when I looked at M42, there were 18,333 submissions by astro imagers all across the world. So lots to choose from, lots to look at. But this is just a snapshot of one page, so you can see all types of orientations, all types of colors, all types of sizes, and every one of those is correct because it was the interpretation of that individual astrophotographer of what he was doing with his data. M51, again, different orientations, different colors, and boy, look at this one up here. This is really an exaggerated color that brings out a lot of contrast in some of the spirals and some of the arms. Specifically, it might show you something that you're trying to outline, or maybe even from a scientific standpoint, but again, every one of those is a correct interpretation of the data that they had. Recommendations. Somebody just getting started, what would you do? Well, most people have some type of a DSLR. So the first recommendation was go out in the backyard, put it on a tripod, do some timed exposures. By all means, you'll need a remote shutter release, whether it's a mechanical one or an electrical one, because if you try to push the button for timed exposure right away, your camera's going to shake and you're going to get a crummy photo. So, you know, especially the moon too, you can take a 30th second or a 120th or a 250th second exposure and get lots of detail on the moon. That's a great target, lots of fun to shoot. There's some small things called Star Tracker, which allow you to put your DSLR and basically track an image. So you can do a timed exposure and get those timed exposures. And here's one that was recently introduced by Skywatcher. It's called the Star Adventurer. And you can see you've got the counterbalance arm, and you can put your DSLR on there and do some really, really nice stuff as far as tracking images and getting started. So start stacking with Deep Sky Stacker. It's free. Photoshop is probably the best thing to start out with. Most people are somewhat familiar with that, and it's relatively inexpensive. And you can do some really, really beautiful photographs. And here's some DSLR photographs. One pointed at the North Celestial Pole, looking at the time lapse of stars moving around the North Celestial Pole. Beautiful image of the Milky Way. Here's M45, probably with a DSLR, maybe you know, 120 millimeter lens or something like that. The Whale Nebula, M31, more Milky Way. Here's really an interesting star exposure with the highlighted background, the trees. Again, this is probably I don't know, maybe a 300 millimeter lens on a DSLR taking a more close up of a galaxy. And here's one of a nebula. Again, probably, you know, 100, 200 millimeter lens on a DSLR sitting on a tripod. So what's after that? After you once get the bug and you become addicted, you're going to want to try something different. And typically what you're going to look at is trying to look at a telescope with a focal length of something under 750 millimeters, whether it's a reflector or a Dob or a Newt or don't really care. You're looking for something that's easy to focus, easy to track, and get you those nice, big, broad, beautiful, wide photos of nebulas and Milky Ways and other types of deep sky objects. And there's just a multitude of those available. Skywatcher, Explore Scientific, Williams Optical, Orion, you list go on and on and on. Lots of choices, lots of variety, reasonable prices, and great, great telescopes, high quality. The thing you want to really concentrate on those, spend as much money as you can on the tripod and the mount, because certainly it'll handle the weight of all these and some of the accessories you put on. But as things change, you add things, maybe add a bigger scope. If you've got an equatorial mount that maybe can handle 40 pounds, you've passed that particular point, and you can just put a bigger scope or a bigger system on that mount, and you're ready to go. And the next step too is look at that cooled astro camera. It really adds a lot to the whole process. Again, ZWO is a great manufacturer. There's a whole variety of them. Lots of good Astro cameras for less than $1,000. Very, very high quality, great cameras. Guiding, external guiding to start out with. And then again, that guide scope in the 50 to 100 millimeter range does a wonderful job. Get the best guide camera you can at the time, because you'll use that later. It'll be something it'll stay with you for a long, long time. And then the guiding software is PhD2 and it's free. So most people use that. I started out with my Canon DSLR with a program called Backyard EOS. It's a free program that handles the image capture with the Canon camera. There's one for Nikon, I think one for Minolta, so a whole variety of software packages that can do that. Started out with Deep Sky Stacker to stack my images and frames. Used Photoshop, now starting to use PixInsight, and spent hours and hours on YouTube. And you really got to be careful on YouTube, because you're going to get a lot of people with a lot of opinions which are wrong. So you really want to pick some mentors who know what they're doing and kind of follow them. And here's some guys that I followed. Trevor Jones is fabulous. He's been doing this a long time. He was one of the guys who's really an expert at Photoshop. He used it commercially in his business where he worked. He's got a number of tutorials, lots of stuff on the web, lots of YouTube videos, really, really good and really credible. Sean Nielsen is a guy from Canada, which I look at a lot. He tends to be a little more direct. His videos are 5 to 10 to 15 minutes, specifically talking about doing one thing and getting right to the quick and telling you how to do it. Kuya the Lazy Geek actually images out of Tokyo in horrible light conditions. And he's a kind of humorous guy, and he does a lot of different things, and he's a good person to follow and very credible. Adam Block, of course, it's the University of Arizona right down the street. Very detailed, very complex. He has a paid subscription service where he has a lot of videos, which I've looked at a lot of them. A lot of them I didn't understand the first time I went through them, but I find myself now going back when I get to a certain situation and then go back and look at it and say, oh, okay, now I get it. I understand what he was talking about, but really, really good. And James Lamb is another good name. He's also very technical, tends to be a little shorter, does a lot of analysis, comparisons, a whole variety of things. Excellent one to follow. But you got to be careful about these two guys, because if you ask them what time it is, they'll tell you how to build an atomic clock. You'll eventually get there, but it might take you a while. So be warned that, again, that's the type of thing that I'll go back to and study them again after I run into a different problem and start to really understand what they're talking about. And Masters of PixInsight are several guys. They have some courses, some monthly webinars. They also have some consulting services, really, really good, competent, capable people. So, I can highly recommend anybody on that list as being very valuable and very competent YouTubers. Here's a typical setup. This is about a 430 millimeter refractor at about 100 millimeter guide scope. And those are some typical kind of high-end retail prices you might see. Now, chances are you've already got the DSLR camera. All it takes is a little mechanical extension to get the right spacing, maybe a $40 item. This is a Skywatcher mount, really, really good mount that can handle a lot of weight. I think it's rated for at least 40 pounds, maybe a little bit more. But, and again, a good Astro cam can go from a couple, $250 maybe to $1,000 will get you a really, really good Astro camera. But that's kind of the next step of a really high quality refractor system that'll last a long, long time. And also, that particular size system is very portable. That's the type of thing that you can take out to a deep sky site, set it up quickly, and then take it down and put it back in your car and be able to transport it. You really want to be prepared to maybe spend about 20% of the cost of your equipment on software and training, because that will mean a lot. It'll make you advance very, very quickly. The courses that are available, like Masters of PixInsight and Adam Block and some other people, extremely invaluable in learning the process of astrophotography and basically not reinventing the wheel because somebody else has already done it. So you pretty much got your honorary degree in astrophotography. Take lots of pictures, stack them with Deep Sky Stacker, process them in Photoshop, and you got those beautiful images. So you've got this success which will get you addicted for sure and carry you on. But you have to remember that your family's going to be amazed because they love you, and your friends won't understand. I'll say, well, yeah, that's nice. So be prepared for that. Pretty much that's it. You're done. Great pictures, great fun. You're addicted, and you're starting in the hobby. Again, back to the first photo I did, which got me started. And a little over a year later, this is the same one I did to the same object. So I think a considerable improvement. Lots of nebulosity here. And one thing that people strive for when they're doing the Orion is that there's a trapezium in the center. It takes a fair amount of exposure manipulation to get that to show up without overrunning it because there's a high dynamic range there. But I look at this photo, I say, well, there's a number of things I can improve, and I can change the stars, or I can do this, and you'll find you'll do that with every photo that you look at, every photo that you've done. You go back to it after you've learned some more things, say, okay, well, that was okay, but I can do better next time, and I'd change this. Here are some, these are one-shot color photographs, either made with the Canon DSLR or that first Astro camera that I got. A whole variety of nebulas and planets and the triplets, but they're all done in my backyard in border light skies, which that was one thing I was concerned about when I got started the hobby. That is, I got really, really crummy light polluted skies, and I'm really going to be able to pick out those images. As it turns out, you can, and really the key there is getting the right filtering to let the light from the particular objects that you're trying to image come through, and then screen out the light of the light pollution that you don't want. Back again to our pillars of creation from the Hubble palette. And we talked about the S, the H, and the O palette of only accepting those particular wavelengths of light that are a part of the object we're trying to image. And these were taken with a monochrome camera with those three filters. And Cigar Nebula and the Pillars of Creation. This one I really like, the Owl Nebula, but you can see a whole variety of different types of images, lots of color, lots of definition, and something you can do in your backyard. This is one I really like. This is basically the Ghost of Cassiopeia and only using the H filter. And I get a black and white image, which I thought was appropriate because it's a ghost and you sort of have that ethereal look. So that was just one filter on one evening. And some more images of various types of things, again, done with filters. But that's really the key to photographing in your backyard, is choosing the right filter to get rid of the light pollution and let the light in from the targets that you're trying to capture. Again, Astrobin, I'd highly recommend you go there and take a look because, again, amateur astronomers from all over the world are posting photos, and it's a great place to learn. And I post my photos up there as well. And that's kind of the end. Really, when you think about it, when you're dealing with a hobby that deals with infinity, it's really kind of the beginning. So there's an infinite number of things that you can do and chase and photograph and continue to expand on. This is something I also posted in the last video. This is the calibration video I did about a year ago. This is the automation video I did, I guess, in December. Basically, push a button and step back and watch your system run all night long and take photos. And the one on top is a link to for tips and tricks. And what I did was, as I was running into problems and finding solutions, I jot those down. I just put them in a document to kind of do some things that I ran into and the solutions I found. Some typical things like oiling the threads. When you put together that image train where you've got screwing something onto your telescope and you screw on the off-axis guider and you screw on the filter and you screw on the phaser and you screw on the camera, aluminum threads, fine threads, like have the tendency to automatically weld themselves. And what you're faced with is getting a channel lock plier and a pair of ice grips, trying to free those up if you want to take them off, which is not really good for delicate optical equipment. So one thing I saw on the YouTube was a guy took a Q-tip, put a drop of 3-in-1 oil in it, very lightly put it around both the male and female threads, took the other end of the Q-tube, wiped off the excess oil that was on there, screwed them very generally together, and they always came apart. They never locked up. So really a simple thing to do, a simple solution. You'll run into those things all the time when you're looking at problems other people have solved. The other one was a guy with a bar of soap. If you take a tripod and then you stick on top of that your mount, you've got two metal surfaces which are not highly machined. They typically have little burrs and ribs on them. So when you put those two together, you try to make your azimuth adjustment, it'll move a little bit and it'll jump. It'll move a little bit and it'll jump. And it's very difficult to get an accurate placement. So people were talking about taking Teflon strips and adhering it to both sides and doing all sorts of exotic things. Like I said, well, take a bar of Irish soap, rub it real hard on the top of the tripod, or rub it real hard on the bottom of the mount, stick them together, and they'll be slick as ever forever. As long as you don't get rained on, you'll be fine. And it's a great simple solution. But those are the types of things you run onto of problems that other people have solved that really take some of the headaches out of the hobby. So what's next? Well, for me, I'm going to try to reshoot some of those targets that I mentioned that I saw that I can improve and try them again and do something better with them. Experiment more with that narrowband colors. Again, take a look at the targets for the next 3 months to see what's coming up. Mosaics is something that's really pretty intriguing, where you take your telescope system, you take an image here, you move it and take an image here, you take an image over here, take an image over here, let them overlap, and then place those all together with software. And now you all of a sudden have a huge field of view. And you can do that not only with 4, but 15 or 20, or if you're real complex, kind of the sky's the limit. So that's something I'd like to experiment with. I'd like to do some stuff on planetary. I know nothing about that. It's kind of a different piece of software and a different process, but I'd like to learn more about that. And the moon is fascinating. You know, you can take a look at that and take some photographs initially with the DLSR, and just lots to look at there. And of course, you're dealing with infinity. So again, thanks a lot. Appreciate the time. We had kind of a late start, but there's my contact information. It'll be posted as part of the presentation. Feel free to get a hold of me. I always love to talk to other people about what they're doing and what equipment and what kind of problems they're running into and what kind of solutions you found. And more than happy and always excited about talking to anybody about the astrophotography, because you can tell I'm booked. So thanks, guys, everybody.
Okay. Thank you, Sid. James, do you have any questions that came in from the web? Yes, we do. Okay. So if you want to.
Sure, I got a question here on how would a Hyperstar accessory on your SCTV or SCT change your technique?
That's a very good question. I did get a Hyperstar, and that's something I use for wide field and catching the big nebulas, because it takes my 2,000 millimeter scope down to 540. It also takes it down from about an f7 to an f1.9. So now my exposure times go down from 300 seconds down to maybe 30 seconds. So now you can get a lot of data in a very short period of time in a very wide field. And I'm about ready to put that back onto my system as soon as the sky's clear, because nebula season is coming up, and there'll be some great wide field type of applications. And that 540 millimeter telescope is a great situation for that. And again, it's at 1.9, so it's super fast, and you can take very short exposures and get a lot of data.
Okay, in the room, any questions? Yes. Just for the folks on the Zoom, we're going to do this.
When you take your flats, do you just take an overexposed part of the sky when you do that? Is it just you just create a more exposure on a blank frame of the sky? Right?
Yeah, that's a really, really good question, taking flats, because there's something called t-shirt flats, where you basically take a t-shirt, put it over your scope, point it at a place in the sky to get enough light to expose those flats again at a fairly high light intensity. And that works really pretty well. It's really pretty simple. A lot of people use an LED flat panel, which is what I use. You know, something from Amazon for about 30 bucks, put it on the top of the scope. You can adjust the intensity of the flat panel so that you get about a 1 second exposure for your flats. And depending upon your filter, you'll have a different exposure time for a red, green, or blue versus a narrowband. So you may have to adjust the intensity. But that works out very well. But the sky flat works out very well, very simple. And then the LED panel works out very well. There's also something called, I don't know the name of it right now, but it's a mechanized system where it flops over on top of your scope, which is computer controlled to adjust the intensity, and it costs you about $1,000. T-shirts are pretty cheap.
Well, thank you again, Sid. We appreciate it, and it's a really interesting presentation. Again, if you want to, because there was a lot of information, Sid's presentation from last month is on the website, and in a few days, the presentation from tonight will be posted. So check the website, and that's a great way for you to kind of slowly go back through the presentation. Maybe you can stop and take notes or whatever. Next month, our August meeting, our speaker will be Don Wrigley. He's going to be talking about lunar observing. So he's our resident lunatic, and should be a lot of fun, because Don really does know the moon very, very well. If you could help us kind of put the chairs away. Nice to see visitors tonight and our new members / visitors. So we're appreciative of that as well. We'll see you next month. Thank you.